All right. Oh, yeah, it's recorded. Good. No problem. Okay, so we talked about a strange design last time, which was the hierarchical design. Today we're going to talk about another strange design, one that's a little more useful and a little less hard to understand as far as interpretation. So this is called the lattice, square. So far we've focused on procedures for dealing with a nuisance variable, right? We've talked about that. We've talked about a blocking kind of experiment, or we talked about repeated measures, which remember is a special case of blocking. So we talked about both of those. You can actually, the other thing you can do, and we'll talk about this in this class, you could learn about it in graduate school, is something called an ANOVA, analysis of covariance. And what ANOVA does is, instead of controlling through design for a nuisance variable, which is what you do in blocking or repeated measures, you control statistically for something. So what you end up doing is you determine how much variance is accounted for by some variable. Okay? And you actually statistically remove the variance that's shared between what's called the covariate. Sort of draw a Venn diagram is the best way to look at this. So you've got a covariate. Let's say it's your IQ score. Okay, that's it correlates a lot of stuff. And we're going to test some kind of educational thing. I don't know what the hell it is. We don't have the wherewithal. Well, we can't actually make blocks when people have exactly the same IQ. Hard to do. But we do know that IQ is going to play a big role in your score of learning something or another, whatever that thing may be. So what we're going to do is find out how much. We can take a look at in this case, it's going to be IQ, the variance in IQ. And then we can take a look at the variance in whatever our dependent variable is. Your test score, whatever, GPA. There you go, that's good. You'd be amazed at how well your IQ correlates with your GPA. We find out the variance where it overlaps. Okay? This overlapping part, and we remove it. And then we do the analysis variance. You got to think of this in a really conceptual way. I'm not going to show you math. Because the math's, I'm just not going to show you math. So that's another way to deal with it. It's a statistical way of controlling for variation rather than a design way. There's nothing wrong with this. It's just beyond the scope of this course. It's something, if you learn about it, you might see the words ANOVA in a paper, and that's all they've done. They just will tell you what the covariate is. They just take out that overlapping variance. Okay? But we're not going to talk about that. I'm just saying that does exist. This is another way to deal with a nuisance variable. Okay? Now, it may be the case, however, that you have more than one nuisance variable, like two of them, for example. So you have two nuisance variables and a third variable. Remember, nuisance variables you're going to measure. Okay, and you're going to put them, people with blocks is what we would typically do. And we have the independent variable, the one we actually care about. So you have three independent variables, two of them being nuisance variables, and one independent variable you're actually interested in. Okay? Questions so far? So you get two variables you can measure, and you're going to block on. And then one you're going to actually care about, that you're trying to find out if there's an effect. So you sort of put the two nuisance variables together. You put one nuisance variable in a row, like usual. We always have the rows of the nuisance variable and the levels of the independent variable. We're going to put the other one in columns. And this is obviously, to me, very exciting with all the exclamation points. It's late in the year. 3 more weeks of teaching, then I don't have to do it until 2016. So. It's a good thing. Okay. So that's not that exciting, but you know. So you get something that looks like this. That's neat. See where that came in? I like that. So we've got rows and columns. Let's move this over a bit. A, B, C, and D are levels of a factor. They're levels of and then I understand this is annoying, and it's not my notation. It's the notation that everyone's always used, so I apologize for that. But these are 4 levels, A, B, C, and D, of some independent variable you're interested in measuring, okay? They are not actually, I know we've used A, B, C, and D as different factors, different independent variables. They're not in this case, okay? They're different levels. There are 4 levels of some independent variable. Each level occurs in each ordinal position. So A occurs first, A occurs second, A occurs third, A occurs fourth, B second, third, fourth, first, etc. Each row and each column has each level once. And remember, these rows and columns, the rows and the columns here, are actually levels of an independent, levels of 2 different nuisance variables. 2 different nuisance variables. So instead of having just one nuisance variable like we have with repeated measures or like we have with randomized block, we have 2 of them, and we're crossing those things. Do you understand the design? I know it's very strange looking. See, once you have 2 nuisance variables, things get a little bit annoying. Because if you wanted to do a completely randomized block with both those blocks literally interacting, so literally crossing with each other, I should have said cross before, you'd need a lot of cells. We don't have that luxury typically. So you need an equal number of rows, an equal number of columns, and an equal number of levels of independent variables. So you get a model that says any score equals the grand mean plus the effect of rows, the effect of columns, the effect of the independent variable, and of course, our old friend error. Or as we're going to call it in this, residual. So think about it. If we had a 4x4x4, or it's called a 4x4, these are called 4, it's called a 4x4 lattice square. If we had that, we have 16 people we need to test. 16 people. That's all. Because each person, each subject is within each, there's one subject within each set, okay? Now, if we were actually doing a 4x4x4, we need 64 subjects at least. So what this is doing is it's allowing us to, what's the word I'm looking for? It's a little more economical, I guess is the word I'm looking for. And practical. And this actually is not a bad design. This isn't like the hierarchical one. This isn't something you would never do. I had a student, 5-6 years ago, maybe a little more. I had a student that used the lattice square. It was perfectly acceptable. It was perfectly understandable. It's a really good thesis too. So detecting noxious odors in pleasant odors. It's really cool. It's Jen Sushar. It's a really, really, really neat thesis. And we have one every 4 or 5 years that shows up, does a lattice square. And it's not a problem. Everybody understands this. It's like sort of a classic experimental design. So the analysis of variance is kind of weird, though. It looks like this. There's an effect of rows, an effect of columns, an effect of the independent variable. So this part shouldn't surprise you. Rows, columns, independent variable, residual, and total. Now, note that there's no interaction terms. Well, there can't be because we don't have every row and every column and every level of the independent variable occurring with every other one, do we? We just have each level of the independent variable occurring in each ordinal position. We can't measure interactions. I'm not saying there aren't any, I'm saying we can't measure them with this design. So you get, so p minus 1, what is p? P is the size of the lattice square. So in our case that we had there, it's 4. So we would have 3 degrees of freedom for rows, 3 for columns, 3 for the independent variable, and 6, 3 times 2. For residual. 3, 6, 9, and 6 is 15, and we have 16 observations. So there p, it's the Latin square of size p. That's the size of the Latin square. Okay? That's all it is. So it's a 5 by 5, p is 5. Okay, so then if it was 5 by 5, it would be 4, 4, 4, 12. 16, 12, yep, that does it. Right, 12. 4, 4, 4, 4 times 3, 12, 16, 12. Yep, that's right. Oh, yeah, Daniel.
What if the rows and columns are not the same?
They can't not be the same. Then you can't do this design. You have, in that case, what's called an incomplete Latin square, which is the kind of thing that shows up as a bonus question in graduate school in a stats test. It can be done, and it really shouldn't be done. It's a design that I've seen, and you always read it going, why didn't you just finish it? So it can be done. The problem is, it's a really good question you're asking. The problem is you don't have every independent variable occurring within every row and column, so you actually don't have a complete. So you have a complete Latin square. So the model itself is difficult. It's difficult to determine. Difficult to determine expected values of mean squares. It's a real pain. Don't do it.
Dave.
Yep.
Where did the P minus 2 come from?
I can give you a simple answer.
Is that a dumb question?
No, it's not. No, it really isn't. If we add this, and this up, and see, so rows, columns, and IV, so P minus 1, P minus 1, P minus 1, we get 3P minus 3. You see that, right? Okay. And then we have that should equal plus something, plus big N minus, that should equals big N minus 1. And the solution to that equation, to that unknown, is P minus 1 times P minus 3. Let's go with that. Yeah, that's the easiest way to explain it.
So it'll always be P minus 2?
Yeah. Yep. So, see, really, this is quick. Now, these can actually be really useful if you can meet their really stringent assumptions. And that's why, as I said, about once every 4 years, someone does one of these. 4 or 5 years. The person, Jen Sushro, who used the Latin square, she had an 8 by 8 Latin square. She needed 64 subjects. If she had to cross everyone with everyone, she would need 8 times 8 is 64 times 8 more. What's 8 64s? 256? No, 512. 512.
Yep.
Okay. Wow, we don't have 512 people in the program, much less in intro psych. She couldn't have actually done her thesis. And the thing is, it didn't really matter. She looked for these results. She found really interesting results. It was actually a very cool experiment, and it worked just fine. And the conclusions are reasonable. You looked at the data, everything was fine. But it would be impossible to do an 8 by 8 by 8. But an 8 by 8 is doable. 64 people, that's a pain to test that many people, but it's certainly a lot of the people in the thesis course testing that many people. By the way, please come to the Honors Thesis Conference on Friday at noon. No, 1. In NW 200. One till about 4, and then there's like a reception afterwards with drinks. It's good easy. Hashtag AUPsych 2015. You gotta have it. It's Twitter. You gotta do that now. If you don't do that, you're behind the times.
Still don't have Twitter.
You gotta come. You gotta get also sign up for Twitter to make snarky comments during the talks. That's what I'm gonna do. Well, not totally.
Who's a silencer?
At Merbrim, you mean? Yeah, she's been on it since 2008, right? Well, yeah, because I jump on everything early so I can get the name D Broad back there. So I can get it before my brother Dan. Yeah. I once signed in. I was at an airport and I signed in to pay for Wi-Fi. It was like $10 for the day, and I was flying back and forth, and my dad was dying. And so I thought, well, I got to do something here because I'm sitting here thinking about how my dad's sick. So I got my computer open, and it says, oh, TELUS Wi-Fi hotspot. And I said, oh, good, well, I have a TELUS phone, so I have an account. but I haven't used it in ages. So I go to sign in, and I sub to D Broadbeck, and it says, forgot your password. Clearly, yes. So I click, and it says, what's your mother's maiden name? And I know my mom's maiden name. So I typed it in, and it said, welcome, Dan. So Dan paid for my airport Wi-Fi that day. Then I changed the security question for him. You never answer those, little tip, this is going way off the other place, but you never ever answer those security questions with things that can be figured out. Your mother's maiden name should be like Mustang 57. Okay, you never ever use something that people can figure out. It's like those questions they have at the bank. It's the first book you ever read. I can tell you one thing. When it asks that question, or it used to, doesn't have that one anymore. They change it up every so often. It ain't a book. And it ain't Mustang 57. All right. So these assumptions are stringent. Equal number of rows, columns, and levels. But if you can meet them, you're in good shape. You can't have any interactions. Remember, that model has no interactions. You're just like with the block design. We can't have, for anyone's block, we can't have interactions there either. You have to have an equal number of levels of rows, columns, and the independent variable. It's not the easiest thing to meet, but you can do it. And as I said, we have one every so often, and it's a perfectly acceptable design. There is nothing wrong with a lattice square. Questions about lattice squares? Yeah, go ahead, Kristen.
Can you give us an example, like when you would use this?
Yeah, I can try. I think of Jen's thesis maybe, if I can remember it. I'm not going to think of Jen's thesis, it's too complicated. Okay, so if we had three, let's go with a three-level lattice square. So if we had let's in fact think of our example we used with the repeated measures design, or the sort of red block, and just put another nuisance variable. So we've got, we're interested in the three study techniques, three instructional techniques. They're A, B, and C. So this would be, we'll call this straight up lecture, and this would, remember that was the flipped classroom approach, and this would be just, I don't know, what was the other one we had? How about just reading? Okay. There's your three different instructional methods, okay? Now we need two nuisance variables. Remember the first nuisance variable we had was, these would be rows 1, 2, and 3, was prior experience with French. That's what it was, because it was French language instruction. So if we had none, and then we had, we'll call it like core French, and then we had people that actually went to French school. Okay? Now, for columns, what's another possible variable that would be a nuisance variable if we were looking at instructional methods? What do you think? How about what year people are in university? I think that's pretty sensible, right? Because, and you guys know this, when you're in first year, you don't know anything. And I don't just mean you don't know anything about the content, you don't know how to go to school yet. Right? By the time you get to third and fourth year, it's like, oh, I understand. This is how university works. I often, with academic advising, tell people, take a first year class. It's a great break in the week. You've never taken history, don't worry. Get the best mark in the class. You know how to go to university. Right? It's nice and easy. So, first year, second year, and third year. Here we go. Now, this is not a great example because we probably could do a 3 by 3 by 3 and get 27 people. But you know what? Maybe it's a pain to do that. Maybe blah, blah, blah. Maybe we get 10 levels. If it's 10 by 10 by 10, 10 by 10, we need 100 people. 10 by 10 by 10, 1,000. Fine. So now what we do is we have rows and columns, and then we have, let's put here, A, and then C, A, B. So we have one person that gets the lecture approach, has no experience with French, and is in first year. Okay? Now, again, that's kind of, it's a little bit of a mundane example, but that's sort of how you set this kind of thing up. And again, a 3 by 3 lattice square, or even a 4 by 4, is probably not something you worry too much about. Probably it's easy to get 9. Sorry, not 9, but a lot more subjects, like 27 subjects. That's easy. When it starts getting to a 5 and 6 size lattice square, well, like I said, when Jen Sushiro had 8 by 8, that's 64 people. 64 people is way easier than getting 512 people. So it makes a lot more sense.
Can you put like 2 people in each group?
You can. That's an excellent question. You can. Then you get rows, columns, independent variable, residual, and within cell. And you're taking it more variance. Yeah, you can do that. You can also do something, that'd be one approach. You could also do 2 squares beside each other. And you would have another level called between, you'd have another thing in your model called between squares. Calculating that by hand is horrible. I'm not even going to show you how to do that. You do it with it's done with matrix algebra usually. It's a nightmare. But you can do that. You can have it with 2 of them. You could do something where you had, I'm going to call it, well, it's not called this, but first I'll say this way, like a Latin cube. Rows, columns, and then depth. That's actually not called that, it's called a Greco-Latin square. And then you can do a 4-dimensional one that really you can't imagine, which has rows, columns, depth, and then a 4th dimension. Again, these are the kind of things that show up in your PhD stats as a bonus question. You know, I just write some stuff down. I don't know. And those are things you see in theoretical statistical journals. You don't actually see those in real research articles. I've seen, though, the first example you asked, Christina, the idea of having more than one subject per cell. I've seen that. There's nothing wrong with doing that. It's not typical, but I have seen that in the literature. That's a good question. Other questions? Okay, so that's not so bad. So we'll leave the Latin square.